In this lesson, we will discuss Bayesian Belief Networks. We will start with revisiting the Naïve Bayes assumption, then work our way through the Bayesian Belief Networks. When we discussed the Naïve Bayes classifier, we made a very simplified assumption. We assumed that the features are conditionally independent given the class. Then we computed probabilities, multiplied them, and used them for classifications. It's true that this assumption works in some cases, but now we are going to see how it's going to fall short because features are going to have dependencies and we need to capture these dependencies and quantify them. Bayesian Belief Networks, or BBNs, use probabilities to capture dependencies between features. So the model is a graph representation where features or the random variables are vertices in this directed acyclic graph. Let's work our way through this example. Suppose that we observed a wet street. This could be due to rain or a sprinkler that was on earlier the day. So the probability of rain is going to depend on the season because maybe we get more rain in winter and fall, while sprinklers are used more during the summertime. And these observations are interconnected because whether the wet street is caused by rain or a sprinkler, it's going to lead to a slippery surface. So the goal is to compute the probability distribution over these vertices in this directed acyclic graph, then use this graph to make inferences with confidence. Abstractly, the Bayesian Belief Network is modeled as a directed acyclic graph. So a vertex can be a root, have an offspring, or connected to other nodes in the graph. For example, season is an independent feature. It doesn't depend on anything else. However, the sprinkler's state depends on the season, and whether the street is wet or not depends on both of the rain and the sprinkler's state. And I want you to pay attention that the values are not simply 0, 1 states, but values that come from a random variable with a probability distribution. And this is very important because when we have the probabilities and capture the dependencies, we can use conditional probability on a subset of these features to make inferences that allows answering specific questions. In this simple example, we have B as an independent variable. A depends on B, C depends on both A and B. To make classifications, we need to compute joint probabilities. Very often we use the chain rule factorization to express the question that we are trying to answer. And as you can see here, computing the probability of A, B, and C involves multiplying the prior probability of B with two conditional probabilities, probability of A given B and the probability of C given A and B. And we need to obtain what is called a conditional probability tables that provides these conditional probabilities, because these probabilities are not just computing by simple counting. Very often these probabilities are results of experiments or observations. And in this example, we have an acyclic graph, so essentially this is not a Bayesian network. Here's a concrete example for a Bayesian belief network with a conditional probability table. As you can see, the lung cancer feature depends on family history and smoker. So in order to obtain the probability that lung cancer is yes, given history yes, and smoker is yes, we go and find the entry from this table. Usually this table is going to give you the positive outcome. It's handy to go and compute the outcome for the negative case, as we're going to need it during the computations. In this example, we have a model for fire alarm system. Sometimes the alarm is triggered by fire or due to tampering. And as you can see, the graph consists of 4 variables: tampering, fire, smoke, and alarm. For instance, if the alarm goes off, there is a probability that it was triggered by a fire or by tampering, or it's also possible that both events happen at the same time simultaneously. That's why it's very useful to look at the conditional probability table and try to make sense what's going on in this graph. An interesting observation: when tampering is true and fire is true, the probability of the alarm going off is not that great, 0.5. And as bad as it sounds, it seems that tampering is working, because even with the presence of fire, we're not getting a high probability for the alarm going off. On the other hand, when there is no tampering, the fire alarm is working just fine. And another interesting observation: when there is tampering and no fire, the alarm seems to go off very frequently, and when there are no tampering or fire, the fire alarm is working as it should be. On the other hand, smoke depends only on fire, so when there is fire, there's a high probability of smoke, and when there is no fire, smoke was not observed. To perform inference, we start by translating a probability question into a mathematical expression. Sometimes we can answer it directly using factorization and the probability table. Other times we might need to apply marginalization or even recognize a pattern that looks like Bayes' rule. So in this example, we are trying to find the probability of fire is true, smoke is false, alarm is true, and tampering is true. We write the expression and start to work our way to find the probabilities. So the probability of fire equals true. Since fire is an independent variable, we have a prior probability. Similarly, with probability of t equals true, we need a prior probability. But for those conditional probabilities, we should be able to look them up from the probability tables. Finally, marginalization means that the probability of an event can be computed by summing the joint distributions of all possible values of other variables. For example, suppose that we want to know the probability of fire occurring. We know that the alarm went off, but the alarm depends on both of fire and tampering. To find the probability of fire, we need to marginalize over the tampering variable, considering both probabilities. Tampering is true when the alarm goes off, and tampering is false when the alarm goes off. Then we use the law of total probability to sum over these probabilities. In summary, we discussed the Bayesian belief networks.